All right, gang, if you notice that homework 7 didn't have any instructions, you're correct. That's why we're going to extend the due date. They're certainly there now. What was the instruction? Do you remember when we did the text generator where you would type in a message that you wanted converted to key presses on an old-fashioned cell phone, a pre-smartphone? We did that to where like an A would be a 2 and a B would be a 2-2 and a C would be a 2-2-2
Tuesday?
and so on. So that was Tuesday's lecture. Yeah, so that was lecture L and homework 7. So the function we were coming up with to do it was this. You can't see the screen. I didn't turn the lights on.
Did you bend the paper back again?
I'm so sorry, pardon me. I didn't do that. I don't know why the screen is tilted again. Somebody must really like the screen being angled like that. Anyways, okay, so in lecture L, we use this code, and we started it off. A, B, C, D, E, and F would print out, you know, the right number of 2s, the right number of 3s, and so on. And it's not the only way you could do it. So if you feel like solving it in a different way, that's fine. Now the code we came up with will do an entire string. If you go back and look at lecture L, I believe it'll go through an entire string. I believe we use getLine to read an entire string, and then we iterated from beginning to end. If that looks a little too complicated, you could just ask the user for 1 character. If you get stuck on that, text me, because it's not that hard to get 1 character. You can either use, I don't remember, but I know we've done it. So if you get stuck on it, I will certainly look it up and send you a reference, or just write it on a piece of paper, send you back a text message showing it to you. So what we're going to do today is talk about bits yet again. So if you have this, what?
Mm-hmm.
If you have this number, let's put quotes around it. And you wanted to figure out what that was in base 10. The places are 1, 2, 4, 8, 16, 32, 64, and 128. So this has a 1 in it. It's got a 2 in it. It doesn't have a 4. It doesn't have an 8. It does not have a 16. Doesn't have a 32, but it has a 64. So that looks like a total of 67. It would be kind of neat if we could write a program that said, what number, right, or just enter a number, right? You'd type in 67, and it would display the bits are 0, 1, 0, 0, 0, 0, 1, 1, right? That'd be cool. At least I think it'd be cool. So the way we're going to do that is there are lots of ways. There's an algorithm you could use where you divide by 2 each time and you take the remainder and you build a string. Or you can just use a method that's already provided for us by C++ called the bit set. Not a method, it's a class. So we could use a bit set. To convert a number to a bit set is as easy as saying this. We can usually leave the std : off because we're using the using statement. So let's give that a shot. Let's go into our code. Boy howdy, I wish it filled in the boilerplate for me, like it does on the newer versions of Visual Studio. We're going to add a new # include for today, which is the bit set. So # if # include less than bit set greater than. Let's just test out their message. Their method, excuse me. Cout less than, and then we'll get a little bit more wild and crazy with it if we feel like it's working well. Bit set, and then these angles means how many bits we want to be displayed. And then the stuff in the parentheses indicates what number you want to convert. And then if we call .toString, it's because we want to store it in a string. But just to display it to screen, we don't even need to do that. So if I can keep my long-term memory going long enough, short-term, excuse me, to type something like that in, cout less than, bit set less than, let's turn it into 8 bits. We only want to see 8 zeros and ones. Parentheses, and the number, what did I come up with? 67, I think, is that number, in parentheses, semicolon. And when I run it, I want to see the same thing that I had in Notepad, which is 010 followed by, 11 at the end. Oh, 111 at the end. Okay, it is working. That is astonishingly easy. That's way easier to do than it was in Java. I'm shocked by how easy that was. Okay, so that's cool. What if you wanted to do the reverse? Well, firstly, let's store it in a string, right? String, well, let's make this a little bit more generic. Int number equals 67. And I'm going to comment that one out. And string bits equals, same business here, bit set all the way out to the parentheses, bit set less than 8 greater than parentheses, number greater than, excuse me, close parentheses, less than ENDL. That's not right. This isn't a cout statement. Dot to string. Let me make sure I get the syntax correct. To underscore string, that's what it is. All right. To underscore string, parentheses in parentheses, semicolon. There we go. Let's print it out. Cout less than, number equals, end quote, less than, number, less than, quote, space, bits equals, end quote, less than bits, less than ENDL. There we go. All right, seems to be working. And just out of curiosity, if we do this, if we go look at Space Invader bitmap, if we were going to try to figure this out, one of these, yeah, how about him? Looks like we could do him pretty easy. So if we were going to number these, that would be a 1, right? This is the 1's column. This would be the 2's column. The 4, the 8, 16, this is fun, 32, 64, 128, it's a little bit wider than a byte. 128, 256, and 512. All right, honestly, those numbers are larger than I want to add up in my head. So there should be a calculator built into Windows that'll let us do this. That'll convert from binary. View, programmer calculator, type my input in binary. So for example, this is going to be 1, 0, 0, 1, 0, 0. I'm going to do horizontal lines for 0, 0, 0, 0, come on, 1, 0, 0, 0. I think that'll be correct. So 1 followed by 4 zeros and another 1 followed by 3 zeros. So according to my calculator, 1, 0, 0, 0, 0, 1, 0, 0, convert that to decimal, 132. All right, let's make a note of these. The top line is a 32. What's the next line? Can we bash this on one side of the screen and get Notepad going in the other, or the calculator preferably? Alrighty, so 1, 0, 0, 1 followed by 4 zeros. 1, 0, 0, 1 followed by 4 zeros. 0, 0, 0, 0. In, oh, I forgot to do it in binary. Fine. Where's the clear key on millions of these things?
It's above the 9.
Yeah, there he is. Thanks. All right. So 1, 0, 0, and then 1 followed by 4 zeros. 1, 0, 0, 1, 0, 0, 0, 0. That making sense? You see what we're doing? This is called a bitmap display. And it's how black and white video games are programmed, or the original Macintosh, which only had a black and white screen, or the Xerox Star and the Xerox Alto, which predated the Macintosh and had a graphical user interface. And so that in decimal is a 144.
So if you're starting with 1 right there, but you have another 0 before that, wouldn't that make that technically 1?
Well, I could have typed in the zeros before it.
Well, I mean, for the first set of numbers that you put down to display where the bits would be at, 1, 2, 4, 8, 16, 32, 64, wouldn't it actually be 1 more to the right?
I could have started there, if that's what you mean. And I could have gone all the way to here.
So it's not going to make a difference.
Well, it would if I wanted a border around it, where I 1, 2, 4, if I'm getting your question, 8, 16, 32,
Yeah, yeah.
64, 128, 256, 512, 1024, 204A.
So with you writing it out how you are now, starting from the top, that extra 0 on the end isn't going to affect it at all?
No, no, no. It's just not going to be displayed when we print it out. And I've already lost. I thought I wrote it down. No, I didn't know where to go. Dadgummit. You can make me add them up again. I don't want to do them all. It's kind of tedious. So that was 1 followed by 4 zeros and a 1 followed by 3 zeros. Okay, great. Clear it. Go to binary. 1 followed by 4 zeros. 1, 2, 3, 4. Yeah, and I lost it. Followed by a 1 and 3 zeros. I swear I've lost it. 264. And let's do one more line. Let's do this one. So 1, 2, 3, 4, 5, 6 ones in a row, followed by 3 zeros. 1, 2, 3, 4, 5, 6, followed by 3 zeros. 1, 2, 3. Make it decimal, 504. Okay, so since this is greater than 8 bits wide, we're going to have to come up with a larger number. And what did we come up with? It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 bits wide. So these are my 4 numbers. Number is equal to that. Yeah, bless you. Number is equal to that. And number is equal to that. So, since this is a terrible lot to type, I'm going to take those lines right there. You know, I don't want to call it string anymore because We've already declared it. But I'm going to paste that there, and I'm going to paste that there, and I'm going to paste that there. Then I'm going to move that back to where it was. Okay? And I don't care about this number anymore, right? Because that's not part of our Space Invader graphic. So now I only want to do oh, okay, fine. String bits. If you comment out these lines like I did, you're going to have to add the word string back there. We should see the first 3 lines of our Space Invader, but only if we change this bit set from 8 to 10. Because it's 10 bits wide now. Wonder why I chose 10. Well, I guess the UFO is wider on the screen. If y'all have ever played Space Invaders, who knows? Alrighty. And there we go. I don't know if that's looking right or not. Yeah. Kinda. Maybe it'd look even cooler if we had more zeros in front of it, because we have 3 zeros at the end and only 1 at the beginning. So instead of 10, why don't we make it 12? Bit set 12. Bit set 12. And bit set 12. Don't think I'm going to use a calculator anymore. All right, we're starting to draw them. We could keep going. If we really wanted to be awesome, we would fill in a solid white block for the 1s and leave it blank, a space for the 0s. Let's see if that's trivially easy or not. So I'm going to go up and do string replace C++ and see if there's a replace function. I don't want one that searches for a position and goes to the end. I'd rather replace all occurrences. So C++ string replace all. How to replace all occurrences of a character in a string. Stack Overflow knows all. Okay, by bringing in a new library, boost. That's way too much work, so we're not going to do that. Okay. So anyways, you get the idea of bitmap graphics. If we were going to display this on the screen with a video driver, we would just leave all the zeros to be black and the 1s as white, or vice versa if it was a white screen with black writing on it. This is the way the fonts were created too, right? Just like the old console app. These letters, right? These are probably like 16 pixels wide, if that, right? And so each letter could be encoded as a series of numbers. All the numbers in that Space Invader could be stored in an array. We're going to be awesome and do that. So let's declare an array of ints. Int, I'm going to just call it invader. Open angle, close angle, equals curly brace, and I'm going to type in these 3 numbers. 264, 144, 264, 144, 504. And I'm going to make a loop that goes through that array. The length of that array is 3. So I'm going to be totally cheesy and just hard code length of 3 into my for loop. For, parentheses, int I equals 0, semicolon, I less than 3, semicolon, I plus plus, close parentheses, open curly brace, num equals invader subscript I. When I say subscript, I mean the open square I, close square. I'm sorry, number. That's what we were calling our variable, unless we create a new one. Let's just go with number. And then we could just copy these things, right? These 2 lines and paste them inside our for loop. And now it's going to just print out the 3 lines again, right? So we're going to see 6 lines. And we could go back and take out, ooh, I apparently have a breakpoint. I didn't mean to have had that. All right, there we go. Right, we see our output again. So we could store our entire Space Invader if we had figured out all the numbers in one array. And it'd be awesome to make that your homework, but I'm not gonna. If you feel like it though, I'll give you extra credit. If you feel like drawing an entire Space Invader on screen, figuring out the entire sequence of numbers and getting rid of these 3 print statements, that'd be pretty cool. But don't do that during class. We got farther to go. Okay, so converting to bits. What if you want to convert back from bits to a number? So I'm going to make a string called S bits, and I'm just going to set it to all ones. 8 ones, because I happen to know that 8 ones is equal to 255, just from dint of having done this too long. 1 1 1 1 1 1 1 1. Okay. And so our number, let's get our number. Int snum equals, and I'm a cheat, go back over here and get the way to convert it back, which is to call bit set that to underscore, that would be unsigned long. But if we just want an int, I'm sure that we're going to be able to stick the word int there instead. So int snum is equal to bit set less than 8 greater than parentheses s bits into parentheses dot to underscore what don't do that, to underscore int open parentheses close parentheses semicolon. Now it doesn't seem to have a to int method. So let's see what methods there are. Dot to, really? Is ulong the only one we got? Okay, fine. Instead of int snum, make it long snum. And int and a long are the same thing in this language. And since it says u there, that means it's an unsigned number. It can't be negative. So I'm going to say unsigned long on this side. Now let's print out the number and the bits again. Cout less than snum less than bits are space end quote less than s bits less than ENDL. Now run it. I want to see that it says 255. Well, I'm not gonna because I have an error. Function call missing an argument. Oh, what did I do wrong? I got so annoyed at I didn't put my parentheses in parentheses there. So on this line right here, that's what that line should be. Bit set angle 8 angle parentheses s bits close parentheses dot to long parentheses close parentheses semicolon. And there we go. Just like that. We could have stored the results in an int anyways if we had chosen to by doing this. We could have just made it an int, but we risk data corruption. However, 8 bits is so far. A bit is 32 bits long, so there's no value in 8 bits that could cause overflow. So if we wanted to store it, we could just do this. Int snum is equal to, and we could cast it. You remember the Python cast, you do in parentheses like that. but you see more often people who learn C first do it like this, parentheses, int in parentheses, like that. And then you'll see an even nastier syntax, but I'm just going to leave it like that. Well, heck, I'll show you the syntax and you'll agree that it's nasty, and it's actually the one you're supposed to use. But that'll work just as well. We took this, which is returning an unsigned long, and on this platform a long is an int, so there's really nothing wrong with doing this. But like I said, it's only 8 bits. If it was 32 bits, we'd have a problem. Or, I mean, longer than 32 bits, it wouldn't. There's a chance it wouldn't fit into an int. But it's going to give us the same answer. Yep. Okay. All right, that casting. If you have one number and you want to cast it to something else, you can do it like this. snum equals parentheses int in parentheses. Let's declare a long, right? Long big num equals 1, 2, 3, 4, 5, 6, 7, 8, 9, 0, 1, 2, 3, LL. Great big number. Too big to fit into an int, so I'm actually going to shrink it down to something smaller than 2 billion. 1 and then 9 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9. That'll fit into an int, which is good because that's what I'm converting it to. So snum equals parentheses int in parentheses big num. That's one way of casting it. That's a C-style cast. Old school, 1970s. And then when C++ was invented, the inventor decided that wasn't good enough. I don't know why, so he did the Python syntax. snum equals int parentheses big num in parentheses semicolon. That's the old C++ cast. And the way we're supposed to do it with the nasty syntax is this. snum equals, and then the word static cast with an underscore between them. Static, like an electric charge, underscore, cast. And then just like we had the angles with a number here, we're going to have angles, an open angle, a less than, int, greater than, and then an open parentheses, big num, close parentheses, semicolon. So that's a static cast. We'd have to Google up to see what a static cast is, but it's a version of casting. And what does casting do? It takes data of one format and converts it to fit it into another. Now the problem with casting is that you can get data corruption. If this number was bigger than 2 billion, there's no possible way it could go into an int. Let's print out our number. Cout snum space quote less than big num less than endl, just so that we can compare the results. It should say 1 billion the first time I run it. Yeah, looks just fine. All three of those conversions do the same thing, so I'm not going to print it out after each one. But what if this was 10 billion? What if I went and I added a 0 there? Yeah, 10 billion became 1,041,041, right? We definitely got data corruption. What if it was 100 billion? Well, the problem is that a long has 64 bits of data, so it can hold a much larger number. There, that's 100 billion. Got 11 zeros. Yep, see, the results are all over the place. Who knows what we're going to get? So, when you're casting, it's upon you, the programmer, to know whether that number will really fit into an int or not. And so I just made an executive decision that since 8 bits is a mere byte and an int is 4 bytes, that there was absolutely no problem storing it into an int. Okay. So, shifting to the left and shifting to the right. What does shift mean? If you had these numbers, 0, 0, 0, 1, 1, 0, 0, 0, 0. Is that 8? I think that's 9. There we go. That's 8. If you had that number and you shifted it 1 to the left, that just means that the bits all go marching 1 to the left. So it becomes this. See what happened? These bits are all going 1. So this is a shift 1 bit to the left. What if we take the same thing and shift it 2 bits? Well, in that case, this 1 and this 1 are going to go over 2. Right? So I can just copy that, but skip the first 2 zeros, tack them on at the end, because it gets padded out with zeros. So that's the answer. That's what happens. What if we shifted it 4 bits? Well, we got a problem. We've already shifted it 2 bits here. So if we start with this, we're not going to like the results so much because we're going to wind up with bits disappearing. Like this. Shift it 4, please. Oh, this was shift 2 bits to the left, right? Forgot to make that comment. So this is shifting 4. I don't know why I'm putting the comment in front of that rather than after it. There. Good thing nobody's typing it. Here we go. Shift 4 bits to the left. What's going to happen? This 1's going to march right off the edge, right? 1, 2, 3, 4. So he's going to be gone, and this is what our answer is going to be. He just fell into the bit bucket, right? He's gone. He's off the edge, and that's okay. That's all we can do about it. It got too large. Now that's if we're storing our data in an unsigned byte, right? That's all that can happen. A byte has 8 bits. If it was an int, we could keep shoving things over until, you know, it fell off the 32nd place. Or if it was a long, you could keep shifting it over until it fell off the 64th bit. So if we shift this number, 000011, what is that? That's a 1 plus a 2. And there's no 4s and no 8s, so that's a 3. Let's shift it once. What is that? Are there any 1s? No. But is there 2? Yes. Is there 4? Yes. So 2 plus 4 is 6. Shift it again. What is that? Add them up. Are there any 1s or 2s? No. There's a 4 and an 8. All right. I see the pattern. 3, 6, 12. It's just doubling each time. So shift to the left is akin to a double. It's effectively doubling the integer each time you do that, right? And so you shift it 4, then you've doubled it 4 times. Understanding that if you exceed your data size, you're going to lose bits. That's just a fact. What about going to the left? It's the same thing as dividing, right? If you have that, what is that? That's an 8. And you shift it. I think I said left. I always get my lefts and rights confused. There's something wrong with my brain. You shift it once to the right, it becomes that. What's that? That's a 4. Shift it once to the right again. That's a 2. Shift it once to the right again. That's a 1. Shift it to the right one more time, and that's 0. So you can see that it's doing an integer divide by 0 each time, right? 8 divided by 2 is 4. 4 divided by 2 is 1. 1 divided by 2, since you have to round down to store it into an integer, is 0. So if you had this number, 1011, and you shifted it 1 to the right, then it would become 0101. Well, what was this number originally? It was a 1 plus a 2 plus an 8, which I think is an 11. And it became a 1 and no 2s and a 4. So that's a 5. So 11 divided by 5 is 5.5 rounded, 11 divided by 2 rounded down is a 5. So again, it's dividing it by 2 each time you go to the right. So shift to the right is akin to halving, right? Or dividing by 2. So how do we shift in C++? I believe we just use the arrows. Let's make sure. C++, bitwise shift, just like that. So let's take a number and just shift it. snum, happens to be a good number, huh, is equal to 64. Int S2 equals snum shift less than 1. It's going to go 1 bit to the left. Int S3 equals snum less than 2. Go 2 bits to the left. And you guessed it, we're going to need our bit set stuff here. I'm just going to go and copy and paste one of these and make the changes. So from up at the top where we were using the bit set stuff, I'm going to do this for snum, and I'm going to do it for S2 and S3. And I have to change this to S2 and S3 as well, right? So, bit set 12 snum. Do we really need 12 bits? No. It's all right. Number equals less than snum. That'll take care of the first one. Bit set 12 S2. Number equals S2. Bit set 12 S3. Number equals S3. And so we should see our original number, and then we should see it shifted once and shifted twice. Just like that, right? And the one's marching. Now, is it deceiving me, or am I seeing the bits in the same place here? No, it's just not padded out correctly. What would I have to do to pad it out correctly? I would have to, use that set W, set width, one of the IO manips. All right, so that's shifting to the left. Shift to the right as you see arrows going the other way. So how many bits was that guy over, right? The one was here. How many would it take to get him to here? 1, 2, 3, 4, 5, 6, 7. Let's shift him 7 times so that he'll be, 1 before the end. Oh, heck, let's shift him 8 so he'll be right at the end. So S3 equals S3 greater than 8. Shift right 8 bits. And then just copy this print statement and paste it. Right? So I goofed. I didn't do it. What did I do wrong? Well, let's just shift it to the 1. What's happening? The number is correct. Oh, I never actually called the bit set business, right? So I need to copy that line and paste it under the assignment of S3, right? Just like that. And then I can go back to setting it to 8 like I wanted originally. All right, and then we're back down to a 1, right? We shifted at 8, and so that 1 ran all the way back to the end of the sequence. So that's shift left and shift right. So those are bitwise operators that work on the bits of a number. Less than is a shift left. Greater than is a shift right, and you just change that 1 to whatever number, you know. I guess if I wanted to get all fancy, I could say less than in and greater than in, which shifts left in bits, right? And shift right in bits. There we go. Now for the idea of bitwise and an OR. We already know about and and OR. We're pretty awesome with and and OR. If we had a truth table for and, it would look like this. If you have false and false, and you're anding them together, then the result is false, right? Because and means that both of them have to be true before your result is true. So false and true give you false. I said or, and. True and false give you false. The only time and is true is when they're both true. If we rewrote that with ones and zeros, it would look like this. 0, 0 anded, but we're going to do a single ampersand to indicate that we're anding the bits. So 0 and 0 is a 0. 0 and 1 is a 0. 1 and 0 is a 0. 1 and 1 is a 1. The only time a bitwise AND will produce a 1 is when you have two 1s. Yeah, so big deal. Isn't that the same? Well, sort of, but sort of not. What if you had this? 0, 0, 1, 0, 0, 0, 1, 1. And you bitwised ANDed it with 0, 0, 0, 0, 1, 1, 1, 1. Let's do it. We stack them up by their columns. And then we just check each column according to that little logic table we wrote. Is a 0 and a 0. What does that make? That makes a 0, right? Another 0 and a 0 make a 0. How about a 1 and a 0? What does that resolve to when you're using AND? And this is our AND table. Well, so is this, right? But a 1 and a 0 make a 0, and a 0 and a 0 make a 0. A 0 and a 1 make a 0. Finally nope, we're still not into the good stuff. 0, and so 1 and 1, finally we get a 1. 1 and 1 gives us a 1. So if we took this number, whatever that is, excuse me for firing the calculator back up, and we turned it into binary, whoopsie, no, clear that. Turn it into decimal, that's 35. So if we print out 35 and this is 15. 1 plus 2 plus 4 plus 8 is 15. If we print out 35 and 15, we're going to get a, what is this? What are those two bits? A 3, right. So 35 and 15 equals 3. So we're now doing math. We're not just doing logic that's true and false. We're doing actual math with it. Now these operations, shift left and shift right, use a different part of the processor than math. Shift left and shift right are about the fastest operations that a computer can do. So it's really far faster to shift something than it is to multiply it by 2 or divide by 2. Weird but true. Although maybe the compiler, you know, switches from one to the other if you have an optimizing compiler like we do to try to optimize it. But anyways, okay. Well, let's prove that. Let's come up here and add those two numbers and see if we get 3, just to make sure that we have any sense. So above my pause, I'm going to say int x equals 35, int y is equal to 15, and int z is equal to 35 ampersand, excuse me, x ampersand y, bitwise and. And let's print them out. C out z equals, end quote, less than z, less than ENDL. And I sure hope that it prints out 3 just like we said. And we did. So why do you care about that? Well, if you have something like this, IP header for example. You know, the bits fly around on your local area network and the internet according to something called the TCP/IP protocol. And the IP header has a format like this. The first 4 bits indicate something, the next 4 bits indicate something else, and so on. Well, how do you get those first 4 bits? You would AND it against 1111 and then 0000, right? Because that would get you the first 4 bits. What we just did got us the last 4 bits, right? We got the last 4 bits, and the last 4 bits of this are those. Well, let's do the first 4 bits. So we're going to AND it against, we're going to take this value, that'll be about the last thing we do today. I wish we had time to do bitwise OR, but we're rolling up to the end of the class. And we're going to AND it against that, 11110000. And just by experience, I'm not going to do that asking whether it does, 1 or 0. I know that it just gives me the result of the first 4 bits, which is 0010, followed by all zeros. That's called masking. I want the last 4 bits, so I'll mask it against the value 15. I want the first 4 bits. Well, again, I don't know what those add up to. Thank goodness for calculators. $240. So if I mask it against 240, I'll get the first 4 bits, which is whatever that is. 1, 2, 4, 8, 16. It ought to be 32 when we're done. So going back here, y is now going to equal 240. Can I type? 240 semicolon. Z is now equal to those 2 things bitwise and together. And let's print it out again. So just copy and paste that line. And I'm going to make a comment that this is equal to 00001111. Last 4 bits, right, of a byte. And that this 240 is equal to 11110000, which is the first 4 bits of that byte. Now, I know I've said this over and over, there's really 32 bytes, 32 bits you can play with in an inch, but let's print it out. What did we expect to get? We expected to get a 32. And we did. So, if we cared, we could print out these bits. We could use bit set to get those 4 bits, or these 8 bits, followed by 4 bits, followed by 4 bits. And this will be the very last thing we do today. So C out, less than, bit set, let me bring this up and put it at the top because it's hard for y'all at the back to see. Or maybe not at the top, but at least a little higher. Bit set less than 8 because we're printing out the first number, which is 8 bits wide. Parentheses, X, end parentheses. Dot 2 underscore string, parentheses, end parentheses, semicolon. Now copy and paste that and just change it to 4 and Y and 4 and Z. Come on, type. 4. I forgot to put an ENDL here, so it's not going to look cool. But I'm not going to put an ENDL here because I want to write out a space followed by bit set again of 4. And this should have been Y on that line, right? And this should be Z on this line. Why do I have an underline there? What's so bad about that? Oh, I have C out there. You're right. I'm spacing out. Here's what I really meant to do. It's just like that. And then an E and DL here. Oh, that's not going to prove a darn thing. Well, forget that. Just print out Z. Why? Because I erased the value of the last 4 bits there. I would have to change variable names and everything to get it to work, and I'm not going to take the time to do that. So Z at this point is equal to the first 4 bits, and we will see that when we run it. Yeah, we didn't even get to ASCII values. Alrighty. Haha, make a liar out of me. Oh, fine. Let's make it 8. I see what I did wrong. Sorry, gang. What if I wanted these bits, these 4 bits, shifted to fill up those 4 instead? I would just shift it to the right by 4 so that those 4 would come marching over to the end. Alrighty, alrighty. I think that's enough about that. I think that we've proven the point. I hope you know what bitwise and OR do now. Even though we didn't do OR, it would. I'll go back to it.
1 or 0.
Yeah. Right. So 1 or 0 works the same way as AND. Right. So if you have 2 zeros and you're ORing them together, that's a 0. Right. 0 or 1 makes a 1. 1 or 0 makes a 1, and a 1 and a 1 makes a 1. The only time OR is false is when they're both inputs are 0. So that's the OR truth table. Works the same way. If you have this 10 10 10 10 and you OR it with 0 0 0 0 1 1 1 1, you're going to get 10 10 1 1 1 1. Right? These bits are going to come down, and then these 4 are going to be all set because of the ORing operation. Because a 1 or 0 is a 1, a 0 and a 0 is a 0, a 1 or, right. So, same business as AND.
Basically, 1 is just true and 0 is false.
Exactly, exactly. And we're treating them numerically rather than logically, if that makes sense, because we're treating each bit as being part of a whole number. So we really have 8 possible true-false numbers in a byte, right? You could actually set 8 different true-false values. The first one means one thing, the second one means something else. If we had time, we'd do that. We don't, so we're going to stop here.